manufacturing, we also would like to see those global emissions, where do they actually come from? So this pie chart here tells us the manufacturing sits over here in industry. But of course, in Indonesia, maybe because the level of industry is not significantly high, they're typically focused in Java, let's say Jakarta, Bandung, Surabaya, for example. But outside those provinces, for example, there won't be too many heavy industries going on, except for maybe small pockets here and there. And of course, another thing that we often see is pollution that comes from this transportation, and that contributes to around 14% of the global emissions. So now let's see if we have some industries or some manufacturing companies, what are the expectations? If let's say we have a company, we have a manufacturing industry. So in Indonesians, I'll put here Indonesian words. Apa yang diharapkan oleh industri manufaktur, ya? First of all, they want to have low production cost. They want to have a reduced production cost. Second of all, they also would like to have reduced expenses. For example, in the energy, electricity, consumables, materials, water. So this is water, ya. Air ini bukan air, ya. Ini water, air, and then delivery. Okay. They want to save some cost in that. And they also want to produce the components as fast as possible. They don't want to have or to wait for too long until they have the product. Another thing they wanted to do is to have many different types of products, yeah, to keep the company alive, to survive. Right. So now let's see on this slide here in the manufacturing, right? I'm going to start with the traditional manufacturing. So all the mining starts over here. The iron ore, the bauxite, the rutile, and all those things for materials. They typically come from mining. It will go into a process called continuous casting. So in these two steps here only, there is a lot of energy required. Okay. So from mining, it goes to continuous casting, which will produce maybe 70 or 100 tons of liquid metal, for example. And then it will go into rolling, for example, cooling, and then further processes. This is a typical traditional processes, the steps in the traditional manufacturing processes. From there, then we'll have this further processes down the line. So from these three main products, from continuous casting, it will go into certain processes. Again, it will require electricity. It will require water, for example. It requires a lot of things. So a lot of energy are actually being used. I'm not saying being wasted here, but I'm just saying being used at this stage, And then from there, once we have the products down here, and then they will have to go to certain processes again. So this process here is called the machining process. So if the material here is relatively big or relatively thick, we will have to machine them down into the size. Okay. So that's again requires some energy, requires some water, requires some cooling, requires a lot of things. Or the process will continue to go into rolling, for example, to make these the shapes, the beams, for example, or some smaller products. Okay, or it will go into this, for example. Let me show you. Let me repeat this one first. It will go also to extrusion, for example, to make something thin, but in relatively short period of time. So all these processes requires energy. Okay, let me focus just quickly on this die forging or forging process here. Di Indonesia itu forging itu apa tuh? Tukang tempa ya, tukang tempa ya. Apa itu tukang besi, pandai besi. Kira-kira begitu ya, pandai besi. Blacksmith. The old names of this forging is the blacksmith. Right. So let's take a look at this one here. This is for the landing gear of an aircraft, for example. So that's an aircraft. It has a couple of landing gears, maybe 4, maybe 3, for example. So the size is relatively big. Okay, and that typically they are produced by forging. They're typically produced by forging because it needs to have very high standard, very high reliability. You don't want this aircraft to land. You don't want this aircraft to land on its tummy, on the fuselage, right? So you want to have a very strong material, very reliable material, right? So this comes from forging. But then before this landing gear is delivered, they will have to do machining. So in this case here, for let's say for 10 kilograms that comes from forging, right? 1 kilogram will be delivered. Okay, so from the time they buy and then to fly, right, around 90% will be machined off. That will become a waste. Now, I hope we can appreciate what happens prior to that, right? So for here, we can see all the energy that we have used, right, to produce that component, for example. And then comes here, we have another processes here, and then comes here, and then we have this component. Now we machine. So the component is ready, yeah, but then we have to machine. Around 80 or 90% will be wasted. Okay, so not just the energy that has been used, but also the material now is wasted. Another one over here. This is a disc for a fan for the aircraft engine, for example. Weight is about 1,000 kilogram, right? So about 60% is wasted. So again, not just the energy that has been used, wasted, but also the material now is wasted. 60%. That's relatively high. Now, so here comes the process called additive manufacturing. The idea is to save the material and also to save the energy. Okay, so here comes the additive manufacturing. So what you saw earlier, they are called subtractive manufacturing, which means you subtract, you machine them, you remove some materials from the component before you deliver. So there is machining process. Okay, here there is no subtractive. There is no material being machined, no material being wasted. And then it can also be used to produce a high complexity parts. Material that can be used in the additive manufacturing, typically they should have good welding properties. Okay, these are the typical materials: titanium, Inconel, stainless steel, and some aluminum alloys. Now, if you compare, or if we compare traditional and 3D printing or additive manufacturing processes, you can see here, first it starts from here, it goes into design, you make the prototype, and if the prototype is good or acceptable, it can go further down to the production, and then you can sell it. But if the prototype is not good, the prototype says, this is too small, this is not strong enough, this is not smooth enough, yeah, it doesn't meet the requirement, it will have to go back here. So you start all over again. So whatever happens here, you have wasted the energy, you have wasted the material, at least two things, plus human resources as well, yeah? Wasted the time. Now, if you follow the 3D printing or additive manufacturing sequence, it comes from here, you design it, you make the prototype, you will not go, or very unlikely it will go wrong, very unlikely. Then it will go automatically into scale. Because at the design stage, you can see everything in 3D, 3 dimension, then before you print it, yeah? So you waste little energy, you waste little material, you waste little time. Right. Oh, why it doesn't want to go change next one? I cannot change to the next slide. Is everything okay here? Yeah, now it does. So this is one example of additive manufacturing or 3D printing. Yeah, you will see very little material is wasted. Let me just start again. I'm sorry, let me put this away. Right, so I will start here. Yeah, this is additive manufacturing. So you make something with very little material being wasted. Maybe some powders being wasted here, but other than that, most material, 90%, 99%, or 95% perhaps, will go into this component. Yeah. So the energy you use to produce this component is not wasted. The material required or needed to produce this component is sufficient. Look at this. This is one of the additive manufacturing techniques, one of the 3D printing techniques. So very little material being wasted. So let me go a little faster. Yeah. Now you can see. So that's the component there. You can imagine, you can imagine if, for example, you have to start from forming, you have to start, or let's say machining. you will waste a lot of materials to produce this component. Okay. Now, machining typically will actually produce a lot of waste material, like scrap materials like this. So it may be 20 to 40% will go into waste. Yeah, only one will go into the production, the delivery. And then for additive manufacturing, very little. You can see here 1 to 2, and then 1 will go into the delivery, the final product. So machining, you have big part like this, a big component, a big material like this, and then you machine this a lot before you can actually have the component. Additive manufacturing or 3D printing, you can print them from zero, like what you saw earlier, and then you make this component, which is very little material being wasted. Next one, you can see here some components that we have actually produced for aircraft applications. Yeah, you can see these are the savings. So from conventional or traditional manufacturing, 1 kilogram. From additive manufacturing, only, let's say, 0.3 kilogram. Yeah, so it saves a bit of material. It saves a bit of energy. You can see it is not significant, not terribly significant, because the problem is they produce small size components. That's the main thing on this additive manufacturing. Let me see, what can I do here now? I cannot start. I cannot produce this. Pak Jatmiko, kenapa ini nggak bisa jalan?
Yes, sir.
Atau ini slide-nya nggak mau jalan, Pak? Sekarang jalan. Oke, so
yeah.
This is the total weight that's actually from the component. Yeah, so it saves quite a bit. Yeah, it saves quite a bit. And then let's say this is for a biomedical application. As you can see here, this is for hip replacement. Yeah, hip replacement, as you can see up here. This is from cast, forge, the casting, pengecoran, kemudian ditempa, dan kemudian di mesin. Ya, so to make this one, you need a big block of metal. Jadi kita perlu material yang cukup besar, bloknya, size-nya cukup besar, baru kita kemudian mesin menjadi bentuk seperti ini. Mungkin sekitar 50-60% material akan terbuang. Nah, tapi kalau kita pakai additive manufacturing, bukan hanya kita save material, tapi juga permukaannya itu kita bisa bikin lebih kasar supaya human tissue itu bisa nempel, kira-kira begitu. Atau ini untuk dental implant. Kalau menggunakan machining process, you will need big block like this, for example. Then you cast, you forge or roll before you machine. So again, maybe 20% or 30% are wasted. But if you use additive manufacturing, you can print this nicely with maybe less than 5% material being wasted. And then you can also make the surface relatively rough. Yeah, look at this. This is relatively smooth. Smooth doesn't always mean good, because our human tissue cannot actually stick to it. Yeah, so that's what they want, rough surface. So you can see how many steps actually is required. Over here, a lot of steps required. You can also see how many materials being wasted. You can also see how much energy has to be used to produce the component. This one here shows the 3D printing for sternum, for our what do you call it, ribs, tulang rusuk begitu kira-kira. Now we can use 3D printing to print this, and this is one component. This is a single component. You can imagine if you have to machine these things, a lot of materials you have to waste, and then it has to be made out of many different components. So jadi kira-kira kalau untuk pakai traditional manufacturing, pakai machining, casting, dan forging segala macam, itu mungkin butuh sekitar 20 part baru dijadikan satu, kira-kira begitu. Tapi kalau menggunakan 3D printing, itu satu part jadi. Ya, ini tuh satu part, nggak ada sambung menyambung, kira-kira begitu ya. Ini langsung jadi satu komponen. Nah, ini untuk robots, kira-kira robotic arm, ini menggunakan traditional process ya, yang di bawah ini. Lihat ada berapa banyak komponen di situ, mungkin sampai 100 komponen, terus ada berapa banyak yang disambung-sambung sana sini, sambung sini segala macam, gitu kan. Nah, yang di atas ini menggunakan 3D printing. Sambungannya cuma 1, 2, 3 kira-kira seperti itu. Ya. Jadi kita menghemat banyak energi dan juga menghemat banyak material. Kesimpulan saya adalah buat traditional manufacturing itu membutuhkan waktu yang lebih lama sampai kepada produksi. Buat additive manufacturing itu membutuhkan waktu lebih singkat. Kemudian traditional manufacturing itu butuh material banyak yang terbuang. Buat additive manufacturing material tidak terlalu banyak yang terbuang. So very little material being wasted. Ini yang traditional manufacturing. Customize itu kita membuat satu yang khusus gitu loh, untuk seseorang misalnya, atau untuk satu komponen khusus. Itu relatif lebih susah. Kalau ini gampang, kita scan, terus kita print, jadi. Ya, ini relatif cukup mahal buat bikin prototype, yang ini lebih murah. Ini increase labor cost-nya, tapi kekurangannya adalah buat additive manufacturing atau 3D printing, itu komponen yang besar, itu lebih susah dibikin. Kira-kira seperti itu. Itu keterbatasan yang sangat jelas buat additive manufacturing. Kira-kira begitu dari saya, Pak Jatmiko.
Ya.
Jadi, terima kasih semua, saya sudah diundang untuk membagikan ilmu saya di sini. Itu saya di situ, tim pasang saya di Oregon. Kalau misalnya ada yang perlu sesuatu, mau connect ke saya, silakan lihat di website Oregon Tech, di teknik mesin. Itu dia. Ya, Pak Jatmiko dan rekan-rekan sekalian, saya minta maaf ya, saya harus pamit karena saya harus presentasi dalam kira-kira 5-10 menit lagi nih buat ke Taiwan.
Oke.
Ya. Tapi kalau misalnya ada yang mau nanya satu pertanyaan, silakan.
Oke.
Misalnya ada yang mau nanya.
Oke, continue one question for Profesor Pasang. I think.
I'm sorry ya, because I have to go. Itu saya juga heran, kenapa bisa dibikin presentasi kok barang banget waktunya gitu loh.
Iya. Terima kasih Profesor. Mungkin ada yang mau tanya khusus untuk Profesor Pasang, dipersilahkan untuk Profesor Haris dan Associate Profesor Dr. C. Prastyadi, nanti kita panelkan setelah Profesor Prastyadi, kemudian kita kasih pertanyaan untuk dua keynote speaker. Tapi this special for Profesor Tim Pasang. Okay, please, any question? One question?
From Widodo, Mas Edwiko.
Ya, oke. Pak Widodo, dipersilahkan. Please. Mas
Pak
Widodo.
Tim,
ya, silakan.
Singkat aja, ini 3D printing itu part of the industry 4.0, right?
Betul.
Ya. Untuk di Indonesia, itu kira-kira kapan bisa diterapkan? Tadi Pak Tim mau ke Taiwan begitu, tapi untuk 3D printing, kira-kira mau diterapkan di Indonesia, kira-kira available kapan itu, Pak?
Kalau sebenarnya satu mesin itu harga kira-kira 1 M. Ya, kami baru order satu mesin buat di Oregon Tech, mesinnya itu kira-kira 1 M. Nah, yang paling mungkin bisa itu punya itu BPPT. Saya sudah usulkan beberapa kali ke BPPT sama ke LIPI, ya. Tolong, ini teknologi terbaru, teknologi yang sangat digunakan sekarang banyak, dan itu banyak digunakan buat apa itu? Buat otomotif, ya, sama biomedical. Otomotif lah paling penting. Kita kan juga kita butuh kendaraan begitu banyak gitu kan, Jakarta macet terus-terusan tiap hari gitu kan. Berarti ada banyak komponen yang kita bisa bikin. Jadi secepatnya setelah ada yang punya mesinnya, saya sangat berani dan saya sangat bisa dan sangat senang kalau misalnya ada yang kepengen minta tolong saya gitu. Pak Tim, sekarang kita udah punya mesin nih, tolong bantu dong, kita bisa bagaimana printnya. Saya bantu. Jadi anytime.
Okay.
Saya bakal punya mesin, mungkin dalam awal tahun depan, early next year I should have my machine. Kalau ada yang mau datang, mau pakai, silakan. Ada yang mau belajar, silakan.
Okay, I think this makes
anytime.
Sense. Yeah. And one thing, can we apply in the what you call it, the processing industrial, just like the cool processing? We have some of tool or maybe some device that we can apply.
Yes.
So using 3D printing, you can use that.
Yeah.
Right?
Okay. Yes. 3D printing is not only just for printing, but it can also be used for repair. So if you have tools that are actually broken, for example, or cheap, for example, you can use 3D printing to print, to fix it. So it can be used for repair. So it is very useful technology.
Okay,
but yes, the initial cost is relatively high because you need the machine.
Right. Thanks so much.
Yeah. Thank you.
Okay.
Thank you for the questions.
Thank you.
Thanks everyone. I will have to go now. Thanks everyone for having me. Yeah. Thank you, Pak Haris. Thank you for your nice talk.
Okay, thank you, Professor Pasang, and thank you so much, and very interesting this presentation. Ya, kemudian kita teruskan. We continue to the third presentation for the Associate Professor Dr. C. Prastyadi. Ya, Dr. Prastyadi in Department of Geology, Faculty of Technology, Mineral Technology, UPN Veteran Yogyakarta. And this title is Geoheritage of Jogja, revealing the lifetime of ancient and modern volcanic art. Okay, please, time for yours, Pak Prasetya.
Thank you very much, Pak Jatmiko.
Okay,
Thank you
25
for
minutes for yours.
Okay, yeah, thank you. Halo everyone, Bapak dan Ibu, Prof. Heris, dan para peserta semua. Let me introduce myself. I'm Prasetyadi, lecturer of Department of Geology, UPN Veteran Yogyakarta. This time, I would like to present title Yogyakarta Geoheritage, and this is a little bit different because this presentation is not a PowerPoint slide presentation. This is a video presentation, and we call our presentation as a virtual field trip to the Geoheritage Yogyakarta. And we are going to several places virtually, and then just like field trip, the team, myself, Ghazali Rahman, and Ardan will accompany you to the several interesting sites. We start our virtual field trip from our campus. This is our campus, the east side of our campus where our faculty located. This is a Faculty of Mineral and Technology building, and this is the situation. There are building of mining and petroleum, and this is in the middle our Technic Geology or Geology Department building. Okay, let's start our field trip. Okay, this is our destination. The yellow pin is our destination. We start from our campus in the north part of Yogyakarta. Okay, this is welcoming
Carolus Prasetyadi. I'm now standing in our campus in front of our department, Geology Department of UPN Veteran Yogyakarta. Welcome to our campus, UPN Veteran Yogyakarta. In the Yogyakarta city, our campus located in the north part of Yogyakarta. And I will be your host in a virtual field trip about Yogyakarta Geoheritage. Come with me.
Okay, this is the title of our presentation, Virtual Field Trip, Geoheritage of Jogja, revealing the lifetime of ancient and modern volcanic art. What is geoheritage? Geoheritage is a term applied to sites of area with geologic feature, which has significant of scientific, educational, cultural, and aesthetic value. Why we generate a geoheritage site or geoheritage location? Because in Yogyakarta, we have 4 universities that has geology department. So we need an area or an outcrop that can be a media or a tool to student to learn directly in the field. So if the outcrop interesting enough and very accessible and very unique, then we can consider the location as geoheritage. Next, please. Okay, Indonesia, especially Java, and the island of another Indonesian island is part of Ring of Fire. Yeah, so the feature of Indonesia, like in Java, is part of the geological feature. This is a tectonic model of Java, where the Indian Australian plate subducted underneath Java and produce a volcanic arc in Java Island, also in other islands like Sumatra, and go all the way to the east to Nusa Tenggara. So we have a very long volcanic island, and it's part of Ring of Fire. In the model in Yogyakarta, because we have a recently we have a earthquake 2006 in Yogyakarta. Then there is a fault in Yogyakarta. So the picture in the left corner, bottom corner, is a representation of model of tectonic of Yogyakarta. So what is the special or interesting part of Yogyakarta? Compared to Sumatra, the producing or the produced volcanic arc in Sumatra lies only in one belt. There is a Bukit Barisan, but in Java we have two volcanic arc or two belt of volcanic. There is a older, the ancient volcanic arc. It is a part of the southern mountain of Java, and then we have a modern volcanic arc in the middle of Java Island. So with the shifting of the old to the younger, then we have the story of the older arc. So this is the special or the uniqueness of Java Island, because to learn the volcano, we don't need to climb the modern volcano until maybe 2000 meters, but we already have like a natural laboratory provided by the erodate the old volcanic arc. So this is a place where we can learn more and much about the volcanic, the old volcanic. Next. So this is the chronology of history of the volcanic of Java. The color indicate the period or the history of Java. We have 5 histories starting from the basement, the oldest rock unit that indicate more than 60 million years ago. And then on top of the basement, we can find erodate of basement, and then we have a period of non-volcanic. So the violet and the yellow indicate there is no volcanism or not yet volcanic period in Java. So with looking, by looking to the yellow, the period of pre-old andesite, we can understand what happened before the volcanism occur in Java Island. And then we explore to the period of volcanic arc, old andesite, that span, the duration is about 30 million years, starting from about 40 million years ago until 20 million later. So the period of the lifetime of this old volcanic arc is about 20 to 25 million years. So what happened within the 25 million years ago, within the red period? Is there any just one event, or there is many or variation of volcanic event or volcanic type of the old andesite formation? So this is the uniqueness or the specialty of the old volcanic in Java. And then after the old volcanic terminated, we have another situation, the new history. There is the blue color period. There is a transgressive limestone river complex platform, yeah, of Wonosari that grow on top of the dying or stopped or terminated volcanic body or volcanic complex. And then move to the 5 to million years ago, we have the modern volcano located in the middle part of Java. This is the situation or the history that we will explore by looking what the evidence of every color or every period. Started with the yellow one, start with the period of pre-volcanic of old andesite. Okay, let's start our virtual field trip. Okay, so this is the situation. We will visit these 5 locations, starting from the older one. That is the yellow. That is the Eocene. So this is indicate the non-volcanic or no volcanic rocks that indicate pre or before prior to the old andesite volcanic arc. And then going to number 2 and so on, and then end up number 5, we go to the end or the termination of the volcanic arc. Okay, let's get start, and we go out from our campus and then go to the first location in the Nanggulan area, yeah, about 70 kilometer west of Yogyakarta city. It takes about 45 minutes to get to this area, Nanggulan area. Nanggulan area is area beside of a long or north-south orientation of Menoreh mountain and located in a plain area that dominated by paddy rice field and the outcrop in the Kalisongo River, yeah, in the area where there is many vegetation. So we need to go to the river, and then we find this location. This is the location of Nanggulan Formation that consisted of bituminous coal, yeah, interlayered with quartz sandstone. So this is no indication of volcanic material. This is related with the basement that give to the quartz sandstone material, and then we have the coal, yeah, indicate the situation of shallow or transition environment. So this is the trip from campus to Nanggulan, yeah, 20 to 70 kilometer, 17 kilometer from Yogyakarta, and now we in the yellow period, yeah, with outcrop consisting of Nanggulan Formation in this area, in the pink area west of Yogyakarta. Okay, again, this is the coal bed of the Nanggulan Formation. Based on the coring or core drilling in this area, the bedding of coal, we can find in the drilling, we have 4 or 5 interbed of coal in the depth of 120 meters. Above the coal layer, there is a quartz sandstone, and within the quartz sandstone, there is a sideritic, and we can find many loads of limestone consisting of time, consisting of fossil, of Eocene fossil, Discocyclina yogyakartae. So this is the indication of timing 40 to 50 million years ago. And the environment is just like this, based on the Ekololono 2000 dissertation, interpreted the Nanggulan environment as part of freshwater swamp and rainforest, close to the sea, yeah, and close to the transition area. Okay, we move to other places. The second site. The second stop site is pillow lava location in the Berbah area. This is about 10 kilometers southeast of Yogyakarta city. And then what we can find here, very specific, very special rocks. Yeah, we can see close to the bridge of the road. So this is very accessible. We can see an outcrop of very interesting rocks. To the right, there is a pillow lava Berbah area. From Nanggulan, we go to the Berbah area to the northeast of Yogyakarta and close to the bridge, so very accessible. Yeah. Now the place already becoming a destination for people, yeah, to have enjoy the beautiful situation in that area. To the right, there is a pillow lava, and to the left is another rock unit. The location in the pink area, yeah, okay, and then we can see in detail the pillow lava of Berbah area. Okay, now we move closer to the outcrop of pillow lava. See, this is very beautiful pillow lava, yeah, with many cracks and the geometry similar to pillow or guling in bahasa Indonesia. And to the right, see, very beautiful, yeah, strongly fractured because it's cool in the water, underwater, so it's cool very fast. So it forms many cracking in the body of the pillow lava. Also in the surface, we can see a glassy surface indicating a glassy skin of the pillow lava, indicating also that the glassy skin related to the fast cooling of the lava when it enters or cooling underwater. Yeah. Very highly fractured, the body of the pillow, very highly fractured. And then to the east, in the east side, we can find different rock unit consisting of tuff lapilli and breccia that has many pumice. So it's produced of eruption material that we call similar formation. So this is the product of the similar volcano. So in this area, we can have the two different rocks indicating two different products of volcanism. The pillow lava related with submarine volcanism, and then the tuff and the lapilli with many pumice fragment related to the other or the different volcanic eruption that we call the similar eruption. Okay, now we go to another places. The next places is the similar volcano. Okay, now we are moving and we arrive to the third place. That is we call this places as tebing Brexia or the hill of Brexia. The Brexia itself containing many pumice. So this destination actually a product of explosion from the similar volcano. The location in the pink. So we are now in the red, but close to the upper part of the red history or part of the old andesite period. Yeah. So this is the outcrop. The black one indicates that the outcrop already weathered, little bit weathered, but still we have many surface that's still fresh, and we still can observe, can see what the composition of the outcrop. The composition of the outcrop mostly of eruption product, the pyroclastic product consisting of tuff, lapilli, and breccia that contain mostly of pumice. In the top, in the upper part, there is a layer, thin layer of very fine ash that indicate a break of explosion. So from this area, we can learn, we can observe what the constitution of the sequence of eruption of the similar volcano, and the white stuff we can see here, the fragment mostly pumice. They're very unique or very special to an explosion product. Okay, so this area indicating a situation of another volcanism or different volcanism, that is the explosion or the explosive volcanism, just like Toba eruption, like what Smith et al. Published in their paper in 2006 and 2011. So this similar volcano, similar in explosion character, but not in type. So this is like Toba, but back to 20 million years ago. Yeah. Okay, our next destination is another product of old volcanism that is the Ngelanggeran volcanism or Ngelanggeran volcano. Ngelanggeran volcano grow on top of the similar pyroclastic deposit. See, there is a white stuff in the left side. The white stuff or the white color of the area indicate part of the similar, the explosive or the Toba type eruption deposit. And then on top of that explosive eruption deposit, we can see the body, the part of Ngelanggeran volcano. Yeah, so Ngelanggeran volcano grow on top of the similar formation. What the constitution or what the composition of Ngelanggeran volcano dominated by andesitic volcanic breccia. Yeah. Okay, from the similar volcano, we go to the south. Yeah, we go to the south of Yogyakarta, and then we can arrive in the area close to the Ngelanggeran, and we can see here the outcrop of similar formation. We can follow the similar formation until this location, and there is the Ngelanggeran volcano. Yeah. Okay. Okay. After, so this is the rocks unit that form or part of the Ngelanggeran volcano. This is, we show the agglomeratic rocks that consisting of block of lava that form a kind of rock that consisting of many blocks. Yeah, and we can call it as the agglomerate. So the agglomerate is part of the Ngelanggeran volcano, like outcrop that we can find in the Ngelanggeran destination of tourism. So Ngelanggeran volcano we interpret as anak Semilir, the son of Semilir, just like the son of Krakatau. So the Krakatau is Semilir, and then Krakatau explode, yeah, and then in the middle, on top of the Krakatau, there is anak Krakatau. So it's we could relate it with the relation between Semilir and Ngelanggeran. Okay, we move to the next stop site, yeah, and then we get to the area in the Kalingalang where we can find indication that the rocks now no longer consisting of volcanic rocks. Yeah, on top of the Ngelanggeran, we can see a rocks that different. Yeah, no breccia, but we can still have a fragment of andesitic. So it indicates that these rocks representing the final or the end of Ngelanggeran period. So this is we call the Sambi Pitu formation, and in Sambi Pitu we can see trace fossil, yeah, trace fossil. So this is not related anymore with active volcanic activity, yeah. So that is the area in Ngelanggeran River. Yeah, the pink is the location, and the history is between red and blue. So we are in the transition between, or we are at the end of the old volcanic. Now we have the blue period. So there is a remain or relic of Ngelanggeran volcano. Yeah. And then after this, we go to the final, and this is indicate a biturbation. Yeah, the sandstone of the Sambipitu indicate the situation close to the coastline, shoreline area. Yeah. Next. Yeah. Okay. Now we go to the final destination. So this is the interpretation of Sambipitu, or the end of the old volcanic arc. So there is the volcanic island, maybe consisting of Ngelanggeran body, remain of Ngelanggeran volcano, and then is eroded, and the erosion deposited as the Sambipitu formation. And to the far, there is a reef that now we can see as part of the Wonosari limestone as the final location of our virtual field trip.
Oke, Profesor
Yeah,
Prastedi.
one location, one location, the
More,
last
yeah.
location, Pak Jatmiko.
Okay,
Yeah, maybe
Please,
just
please, yeah.
1 minute, 2 minutes. Yeah.
Okay, never
Okay,
mind.
this is the situation from the final location. As we can see, the platform area is part of the blue period, or the limestone period of the open marine, yeah, reef complex, yeah, that grow on top of the eroded or erosion of volcano of Ngelanggeran, yeah. So this left is to the south, and then right to the north there is a body of eroded Ngelanggeran volcano. So we can interpret the situation like the paleogeography of the situation starting from Ngelanggeran. Yeah. Okay, this is the area where we can see the platform of limestone Wonosari on top of the Ngelanggeran formation. Yeah.
I'm standing in the location where we can see an outcrop of Miocene limestone of the Wonosari formation. This limestone indicate that we are get into the final location or the end of our virtual field trip in this Icemine of 2021. I hope you enjoy our field trip this time, and we will explore again location of geoheritage, the other location of geoheritage that make our virtual complete to understand fully the geoheritage of Yogyakarta.
Okay, now this is the paleogeography. This is a situation where the volcano is still active in the sea. So this is a volcano that grow in the sea, and then volcano terminated, eroded, and become the Sambipitu with the biturbation trace fossil, and then the blue one is the full the situation where is the Wonosari limestone deposited on top of the eroded mountain or eroded volcano. Yeah. Now we have 20 geosites for preparing to become the Yogyakarta new geopark. So we are proposing the Yogyakarta geopark based on our 20 geosites. Okay, thank you. And there is a one-day field trip. Yeah.
Next time. next year in Icemine 2022.
Okay, thank you, Pak Jatmiko.
Yes.
Yeah, I think it's
Thank you very
Finish.
much, Professor Prastyadi, and very interesting presentation and video one-day trip in Geoheritage Yogyakarta. Ladies and gentlemen, there are many 20 interesting points of Geoheritage of Yogyakarta. For example, Tebing Breksi. This location before COVID-19 received income about 4 billion per year. Yeah, very interesting. And in Yogyakarta, we have many 20 interesting point. And in Geopark Gunung Sewu, about the last of 2020 income in International Geopark Gunung Sewu about 34 billion per year. Yeah, very interesting. And thank you, Professor C. Prastyadi and Professor Ron Harris. And now, maybe any question for Pak Prastyadi and Prof. Harris. Please, audience. Any question? We have 15 minutes for question.
Mas Jatmiko,
Ji, please.
may I ask a question to
Okay,
Pak
Mas Widodo Margotomo, please.
Thank you very much for the time. Pak Ron, it's very interesting when you
For
first.
yeah, Professor Ron Harris, eh? Okay, please.
Yeah. Is it possible to distinguish the potential and the magnitude of the earthquake that creating the tsunami, especially in the South Java?
Yes. We have to make some assumptions, though. For example, we know how much stress has accumulated along the plate boundary,
Mhm.
and we don't know exactly how it's going to be released. It could be released in a series of small earthquakes. I mean, relatively small, meaning magnitude 7 to magnitude 8, which is what Java Trench has been doing ever since we've been recording the earthquakes there. But that's only for the last 60 years. And we have evidence on the south coast of Java, south coast of Bali, south coast of Lombok, the island of Timor, and the island of Sumba for 2 major tsunami events that affected that entire part of the Sunda Trench that are both the same age. So the youngest one is around 500 years old, and the older one is about 1,000 years old. And those demonstrate that it's possible for the entire Sunda Trench to rupture all at once, instead of producing small events, relatively small events like 7.8, like the earthquake in south of Chilachap in 2006, and the earthquake in 1994, which were about 7.5 to 7.8. We have evidence that the Java Trench has ruptured its complete length, and so based on that estimate, if it ruptures the entire length at once and releases the 35 meters of strain that it has accumulated, then that would be a magnitude 9 event.
Yeah.
Okay.
The age analysis of the earthquakes is very uncertain because we have to use optical stimulated luminescence to get the age, and there's always large uncertainties. So there could have been 3 or 4 huge earthquakes that produced those deposits, or there could have been one. But either way, there would be enough energy released during those earthquakes to cause intense shaking in Java. And most of the buildings in Java would not be able to withstand that and would collapse.
Mm-hmm.
Okay.
That's right.
Ya, Profesor Harris, Mas Widodo, cukup?
Yeah.
Okay.
I think it's very great. That's good. We get the information clearly from Professor Harris. As I mentioned, we can distinguish between the potential and the magnitude. I think it's great because we are going to extensively campaign the 2020 principle, right?
Yeah.
Baron, when we know the area that got the potential and the how big the magnitude, is that possible also that we can make the something like dynamic simulation of the earthquake and tsunami, and then we can socialize to the community that is very related to the 2020 principles. Is that
yes? We have done the simulations. Let me just share my screen and I'll show you. So I showed a map right here. We have done simulations of the rupture of the entire Java Trench. You can see it right there. So that's where the earthquake we simulated is. And each one of these locations on the south coast of Java and Bali and Lombok and Sumbawa and Sumba and so on show the height of the tsunami in blue and show the number of people that live in the inundation zone.
Yeah.
And so we have done the simulations, and these maps I've made available to the BMKG and to the BPPD, and they should be the basis for disaster mitigation activities. They also, each one of them has a time series here that shows when the wave should arrive based on the simulation and how high it should be.
Okay, that's good.
And then we also have movies that show the step-by-step arrival of the tsunami and how far it inundates based on Google Earth images like this, where you can almost find your house in this and see how far the tsunami, how close it gets to where a person is. We also have an app that uses Google Earth and uses Google Maps. You can put in your address, or you can put a dot or a waypoint on the map, and it'll show you how long it would take for you to walk quickly from your place to the nearest evacuation site. And so people can actually get feedback on whether they are in a safe place or not, because if it says that it takes 40 minutes for you to get there, then it's not going to work. You're going to have to move to a safer place.
Yeah. That's
Okay,
great. Yeah.
Thank you,
Thanks, Pak Ron.
Pak Widodo and Professor Haris. The last question, one question more.
Thank you very much, Pak.
Yeah, you're welcome.
Halo Pak Jatmiko.
Ye, silakan Pak.
Halo
Dari?
Pak Pras.
Okay.
This is Adi speaking.
Yeah, Dr. Adi Sulaksono, please.
Hello Pak Pras. Thank you very much for your great talk and for your amazing project, especially the way you educate people with using such geoheritage. So when I was at a geosite, it was surprising that even local people understand the geological story very well. So my question is, how did you manage to deliver such a geological story to the common people, which we know they don't have enough knowledge of geology? Thank you.
Okay, please, Dr. Prasetya.
Okay, thank you for the question, Adi. Yeah. And congratulations for your achievement, yeah. A PhD from Penn University, Akita University. Adi is to be back to 5 years ago, part of our team to generate the activity for geoheritage of Yogyakarta. I think with the adding or the addition, the more and more geosite we can propose to the government. Until now, we already have 20 geosites that initially start from maybe just 9 geosites, and now with the help of local government, we now have 20 geosites that covering after that, that cover all outcrop that indicate all period or history of the geology of Yogyakarta. I mean, start from the yellow color history period until the new one, the modern volcano. Like in Merapi volcano center already built a conservation of 2010 eruption area, so people can learn about what happened in 2010 big eruption. So with the involvement of local government, involvement of group of community of or people, local people that we call Pok Darwis. So a group of geotourism, consisting of youngster or young generation from the local area. I think we start or we already get to the point where the geoheritage now become part of a community. So people getting more and more involved in our movement or our activity to socialize the knowledge of geoheritage of Jogja to aims or with purpose, proposing to increase the knowledge of people, especially related with the volcano activity, because the volcano activity related also with the situation where Java is very vulnerable to the earthquake. So earthquake and a volcano is one package of risk that people have to know about the situation. I think we are now get to that point, Mas Adi. So we are ready to propose a new geopark of Yogyakarta, and hopefully with the geopark, then we can have a model of conceptual model of developing or development of community related with high conservation sense of conservation of a community itself. I think we move to the better situation, Mas Adi. Yeah.
Okay. Yeah. Thank you very much, Pak Pras. Good luck with your new project, and hopefully it will be a good geopark or something like that for the future. All right. Thank you, Pak Jatmiko.
Okay, thank you, Dr. Adi, and thank you so much for Professor Ron Harris and Associate Professor Dr. C. Prasetti. Interesting for presentation, and time is up, and I'm sorry for any shortcoming, and time for Master of Ceremony. Waktu saya kembalikan, dan kita beri applause untuk Profesor Ron Harris dan Dr. C. Prasetti.
Thank you.
Thank you, Ron.
Thank you,
Yes.
Profesor Ron Harris. Thank you.
Terima kasih, Chadmiko.
Ya, terima
Yeah.
kasih, Profesor Harris.
Chadmiko, we need to go motorcycle riding again.
Yeah.
like in Timor, yeah.
Like in Timor, Professor. Yeah. Okay, welcome to Yogyakarta again in department,
Alright.
my department. Yeah.
Terima kasih banyak.
Ya, terima kasih Profesor, dan sehat selalu. Ya.
Ya.
Oke, waktu saya
Terima kasih.
kembalikan Mbak Dayu dan Mbak Sarah. Thank you, and I'm sorry for any shortcoming. Monggo Mbak Dayu, Mbak Sarah.
Oke, thank you
Silakan.
very much, Dr. Jatmika.
Halo.
Oke, hello Mr. Jatmika, can you hear my voice? Oke, thank you very much.
Halo,
Dr.
Miss Dayu,
Jatmika Setiawan.
Miss Sarah.
Thank you very much. Is it clear? Okay,
Okay.
thank you very much, Dr. Jatmika Setiawan, and all speakers for insightful knowledge. This event sponsored by PT Studio Mineral Batubara, Pusat Studi Mineral and Energi, Riung Mining Contractor.
We are now entering break session. This break duration will take about 15 minutes, and we will continue to the second session at 10:45 Western Indonesian time. Stay tuned and don't go anywhere. Welcome back, ladies and gentlemen.
Now this is the time for us to entire presentation from our keynote speakers in the second session. Professor Toshifumi Igarashi, Dr. Charlie Totabelin, and Dr. Umar Faruk Ugurlu. This session will be moderated by Dr. Sofa. Dr. Sofa, an academic lecturer with a demonstrated history of working in the mining industry, skilled in mining technology, hydrogeology, and clean coal technology, having a PhD degree in the Sustainable Resources Engineering from Hokkaido University, Japan. Currently engaging research on developing microbially enhanced coal bed methane and subsurface cultivation and gasification concept. Hello, Dr. Sofa, can you hear my voice? Okay, how are you today?
I'm fine, Dayu, Sarah. Really
Okay.
good.
Okay, are you ready for this session?
Sure, 100%.
Okay, Dr. Sofa will lead discussion for Q&A session after the keynote presentation. Please welcome Dr. Sofa Rijalul Haq.
Well, thank you very much, Dayu, Sarah, for inviting me as moderator. And here, ladies and gentlemen, Honorable Lecturer of UPN Veteran Yogyakarta, and also Dean Faculty of Mineral Technology, UPN Veteran Yogyakarta. Good afternoon, everyone. My name is Sofa Rijalul Haq. You can call me Sofa, very simple. And I'm a lecturer of Mining Engineering Department of UPN. And first of all, I would like to thank all participants, speakers, and the committee for your valuable time joining this event. And here in this session, we have 3 main speakers, best scientists and experts in their field from all around the world. And the first speakers we have here is Professor Toshifumi Igarashi of Hokkaido University. He is my supervisor when I was pursue my doctoral degree in Hokkaido University, Japan. And also the second speaker is Dr. Carlito Baltazar Tablin of University of New South Wales, Sydney, Australia. And he is also my senior in Hokkaido University. And then the last speaker is Dr. Omar Faruk Ugurlu of Istanbul University, Cerrahpasa, Turkey. And then here we go. Let's get to the business. Professor Igarashi, how are you?
Hello, can you hear me?
Yes, of course. Are you ready for today?
Yeah, I'm very fine, but I'm not in Sapporo. I am in Tokyo. So from Tokyo, I will make a presentation.
Oh, and then I heard something from Pak Tamamura-san that you have new role for the president of Horonobe Research Institute. Congratulations. Really?
Thank you very much. But it's very difficult for me to move from Sapporo to almost Russia.
I see.
Horonobe, yeah.
Anyway, omedetou gozaimasu, Igarashi Sensei.
Thank you very much.
Then Igarashi Sensei, his expertise focus on environmental remediation based on the assessment of soil and groundwater contamination caused by heavy metals. The treatment for wastewater from closed and abandoned mines, and also his focus on environmental restoration of former mine sites. And also, if you see Google Scholar, you can see his publication, many publication with more citation, maybe more than 2,000 citation, maybe. But actually, he is originally from Hokkaido and was born from Hokkaido, maybe, and also grew up in Hokkaido and has the academic degree from bachelor and master and doctor from Hokkaido University, and promoted to be a professor in 2008 in Hokkaido University. Now, let's hear some insight from Professor Toshifumi Igarashi. And the time is about 30 minutes, Sensei. If you use your 30 minutes, so there will be no answer and question session. But if you use 25 minutes of presentation, you can save 5 minutes for question and answer. So let's hear some insight. Please welcome Professor Toshifumi Igarashi.
Thank you very much so far. So today I'm very happy to join the conference. So can I share the PowerPoint file?
Sure, Sensei, no problem.
Can you see the file?
Very clearly. It's clear, Sensei.
Okay. So I will start my talk. So good morning or good afternoon, everyone. I am Toshifumi Igarashi, Faculty of Engineering of Hokkaido University. Let's change the point. Yeah. So I'm very glad to have a chance of this presentation from Tokyo, Japan. So as so far introduced, I'm very interested in the remediation of contaminated site or treatment of abundant mine water. So, but today's topic is characterization of groundwater flow in a limestone quarry by geochemical investigations. So, Kim Yin is the co-author. He is now work for Cambodia Institute of Technology. And Megumi Kondo, she works for Mitsubishi Materials Corporation, Tokyo, Japan. So this is a study site of a limestone quarry located north of Tokyo. It takes about 2 hours from Tokyo by train. There is a mountain and 3 companies, A company, B company, and C company are concurrently excavating limestone in this mountain. We can see the slope on the top of the mountain. The slope is 2.1 meter wide, 400 meter high. In this mountain, displacement of slope has unfortunately been observed at the around of the center of the slope. So this is the illustration of the plan of excavation. Geology of the mountain consists of 2 layers. Limestone layer, this blue area at the top, and the greenstone layer here at the bottom. In addition, there is an interbedded layer around here between the 2 layers. The residual limestone slope here has an angle of about 45 degrees and 20 meters thick. So these are the monitoring locations at this slope. APS, automated polar system, and the GPS are located at the 1,000, 2,000 meter level here. The displacement of a feature is measured at 1,010 meter level, and the groundwater levels are monitored at the 3 locations here. In these groundwater monitoring wells, appreciable changes in groundwater level has been observed in these 2 wells among 3 wells. This is the relationship between groundwater levels and the rainfall. This blue figure shows the daily rainfall ranging 0 to 200 millimeter per day. The other, the change in groundwater level ranging from 0 to 50 meter. From this figure, the change in groundwater level corresponded to the rain. In particular, the change at 1,000 meter level was extremely sensitive to the rain. So this shows the example of change in rainfall and displacement. When rainfall is higher than 20 millimeter per hour, the displacement of the slope increased dramatically. This is the picture of the displacement measurement here. At one fracture is located around here, and among in the fracture, so we are measuring or monitoring the displacement. So this layer correspond to the interbedded layer. That is, when groundwater level increase due to heavy rain, the displacement around the interbedded layer occurred. This means that the control of groundwater level required to stabilize the slope stability. So this is a conceptual model of groundwater flow by considering the result of the displacement. There are three groundwater flows. Groundwater flow in the limestone layer here, groundwater flow in the base rock, in the greenstone, and groundwater flow in the interbedded layer. Since the hydraulic conductivity of the interbedded layer is higher compared to the other two layers, that's why the groundwater flow in the interbedded layer here is very sensitive to the displacement. Thus, the groundwater level in the interbedded layer should be controlled. So that means the water level here controls the stability or displacement of the slope. So to prevent the failure or collapse of the slope, the company laid pavement of the surface of the mountain to protect the infiltration of rainfall, and constructed embankment made of limestone. And then they excavated drift and boreholes to drain groundwater and insert steel piles to stabilize the slope. So the displacement of the slope gradually diminishing. However, small displacement is still continuing. In general, rock slope failure are triggered by several factors, as you know, such as groundwater, rock weight itself, and earthquake. In this quarry, the effect of groundwater on the stability of rock slope is very important. Due to intense rainfall, like typhoon, the groundwater level rises. That increases the pore water pressure of the slide surface, which lead to unstable slopes. However, groundwater flow in limestone quarries has not well known so far in this site. That makes it difficult to lower the groundwater levels efficiently during intense rain events. Because we do not understand which boreholes, which locations efficiently drain the groundwater level along the slide surface. Therefore, it's quite important to understand groundwater chemistry around the slide surface of limestone quarry. Conventionally, we measured physical parameters like displacement or some stress of the mountain. But we applied a new approach using geochemical aspect to characterize the site and then to drain or extract groundwater efficiently to prevent the stability of the slope. So the purpose of this study first to clarify chemical properties of groundwater depending on the layers, to identify the groundwater in and around the interbedded layer for stabilizing the slope by using geochemical and statistical analysis. So this is the location of the limestone quarry here. This is Tokyo, Sapporo is here. This is the geology of the quarry. The geology of quarry is divided into 3 rock faces or layers. That is limestone, greenstone layer, other alternation between the 2 rock layers. As shown in cross-sectional view of quarry, the cover rock is limestone. The bedrock is greenstone. And the alternate layer exists here between limestone layer and greenstone layer. According to geochemical analysis of these rocks, the calcium content of the limestone was around 55% of calcium oxide as CaO. That of greenstone is around 8% of CaO. And that of alternated zone here, the calcium content ranged from 8% to 53%. So we understand the geology, but how we extract groundwater efficiently from this interbedded layer. In this figure, we constructed underground tunnels at several elevations. Here, here, here. And the green dot here correspond to the sampling point of groundwater, and the red lines, these red lines show boreholes for draining water. Sampling campaign were conducted from December 2014 until now. And the groundwater samples were collected 3 layers limestone layer, interbedded layer, and greenstone layer. So these are the representative pictures of sampling point. So we collected groundwater sample in underground tunnels. During the sampling, we measured temperature, pH, electrical conductivity, and oxidation reduction potential were measured. In addition, flow rate of groundwater from each borehole was also measured. Groundwater samples were then filtered using 0.45 micrometer filter like this. And then we brought all the groundwater sample to our laboratory and analyzed these ions and elements. Then by using the obtained data, geochemical model we used to frequency was applied to calculate the pressure of gaseous carbon dioxide and the saturation index of calcite, one of the dominant minerals in the quarry. So these are the data of temperature and pH, a little bit complicated figures. But I just explained a little bit. L legend means groundwater in the limestone layer, whereas S legend means groundwater in the greenstone layer. From these figures, the temperature in the greenstone layer were very stable, and the pH was a little bit higher in greenstone layer compared to the pH in the limestone layer. This is the result of ORP and EC. ORP, oxidation reduction potential, was oxic. That means these samples are in oxic conditions. And almost the same values are obtained irrespective of the layers. The EC was higher in limestone layer compared to that in greenstone layer. This is due to the dissolution of calcite in the limestone layer. So we also measure the flow rate of groundwater. We found the flow rate in the limestone layer fluctuated depending on the sampling day, whereas those in greenstone layer were stable due to its lower hydraulic conductivity. So this is the hydraulic conductivity in the greenstone layer, base rock layer, and this is in the limestone layer. Then we draw a Piper plot of groundwater samples. Unfortunately, all the samples are located in here, calcium bicarbonate type, irrespective of geology. And this means the difficulty in distinguishing groundwater where it flows by the type of groundwater chemistry. So in this figure, we just consider the calcium concentration change with time. Groundwater samples in the limestone layer exhibited higher calcium concentration than those in the alternate layer and the base rock layers. However, calcium concentration of this, so that means L7, L11, S3, and S4 Those samples are between the limestone layer and the salty greenstone layer. So by using the characterization of the chemical property of the groundwater samples, we can identify the groundwater in the interbedded layer because this groundwater has the media, the calcium concentration is between limestone layer and the base rock layer. So this is the calcium concentration versus bicarbonate ion. In this figure, these four groundwater samples are also located in the limestone layer and the base rock layers. So then we can identify by using this plot, we can identify the groundwater in the interbedded layer. The next point is how we extract efficiently of these groundwater to reduce the groundwater level and then increase the stability of the land slope. So to quantify, quantitatively identify the groundwater in the interbedded layer by using obtained data, geochemical model, frequency, and also statistical model, statistical approach, hierarchic analysis, and principal component analysis were applied to clearly distinguish the groundwater. So this figure shows the partial pressure of carbon dioxide. This dotted line here shows the atmospheric carbon dioxide. Groundwater samples in the limestone layer exhibit excess partial pressure of carbon dioxide compared to the atmospheric carbon dioxide. Those in the base rock layer are undersaturated. So by using the geochemical model, we can distinguish the groundwater in the interbedded layer. This also shows the saturation index of calcite. So groundwater samples in the limestone layer were supersaturated, while those in the base rock layer were undersaturated. So this is the dendrogram of hierarchical cluster analysis, HCA. From this figure, we can clearly understand there are three clusters. This means all groundwater samples were classified into three statistically significant clusters: groundwater in limestone, groundwater in greenstone, and groundwater in the interbedded layer. Even if they have a similar type, that means calcium bicarbonate type groundwater, by using this method, we can clearly distinguish the groundwater. So to sum up my presentation today, by using the monitored groundwater geochemistry from a limestone quarry and calculated result by frequency and statistical analysis, we found the following. A water-rock interaction in the quarry was distinguished by individual layers. all of which are geochemically involved in carbon dissolution, calcite dissolution. That means the water type is calcium bicarbonate. The groundwater sample are classified into original groundwater from the limestone layer, mixed groundwater along the interbedded layer, and original groundwater from greenstone layer. In addition, when we apply geochemical model or statistical analysis, we can clearly identify the groundwater characterization. Then we should extract groundwater in the interbedded layer more effectively, more efficiently, to resulting in more stable slope in the mine site. Thank you for your listening. Terima kasih. Thank you.
Thank you very much. Sama-sama. Professor Toshifumi Igarashi. That's from Toshifumi Igarashi Sensei. Thank you very much for your insight. This is actually, I know this research because actually I went there, Sensei, in Saitama with Kiim and also with Fujinaga. Twice
Really?
I went there.
Have you been there before?
Yes, I also met Kondo-san in Saitama.
I see.
So that is very interesting research because we know the effect of groundwater stability with rock slope with new approach, and then I think that's a novelty approach. It's about with geochemical and also statistical analysis, and it's the first one in the world, I think. And maybe actually the time is about already 20 minutes, Sensei. So I think the question is, the answer for question time is up, I think. But I will let for participant, if you have one or two questions to ask in detail about what Igarashi Sensei presents today.
Any question and comments are welcome.
Yes, please.
May I ask in some questions?
Yes.
Sure. Please.
Yeah. May I introduce my name is Yudi Risyanto. I'm a lecturer in UPN Veteran Yogyakarta. This is very interesting subject about the groundwater, and we integrated with the slope stability. Okay, for the question is, we know that limestone is very sensitive about dissolution, about the diagenetic process, and we know there's some area like Vadose area, kemudian and then phreatic zone, marine phreatic or meteoric phreatic. How about significant diagenetic in the area of study affect with the water flow rate? Like we know if there's some crystallization or leaching process, so the connectivity is not good, so the water flow is maybe decrease. How about in this study area? What type of diagenetic process in this study area, Professor?
Well, thank you very much for your difficult question.
Sorry, Sensei.
So I'm not a geologist, so I'm not sure the diagenesis in this site. But this is one case study of the stability of landslide. So slide collapse, slope collapse. So so as you mentioned, so there are other aspects. So for example, the base rock is consists of aluminum silicate. So that means the silica concentrations are a little bit higher. but not so high, just a few milligram per liter level. But this we can distinguish the groundwater with or without silica.
Okay.
And also we are now approaching the groundwater. It's as you mentioned, it's very not so easy to measure the flow rate, because the companies try to extract groundwater as much as possible.
Yes.
So one idea is to get the data of dating of groundwater flow date. That means we are now measuring the tritium data, tritium H3. And then tritium concentration indicate the retention time in the groundwater, in the geological condition. So by using the tritium data, we are now dividing the groundwater, which groundwater is originate from base rock, and which groundwater is from limestone or the rainfall. We can apply such isotope method in this site. And also, this is just one quarry site. But now, due to the global warming, so this groundwater in limestone area is very sensitive to the global warmings, and also sensitive to contamination of VOC or fertilizer and heavy metals. So based on this knowledge, we should apply this knowledge to the other contaminated site, or very sensitive carbon dioxide sensitive areas. So that will be the next problem in our area. So I cannot directly answer your question. Just I add some comment.
Yeah,
thank you.
Because for information that we know that in limestone we have a connected pore and not connected pore. So the water flow will be affected with that kind of thing. What pore type is connected or not, based on the physically of the limestone. Is that interbed or river? So it's maybe some suggestion maybe for the next program, Sensei could extinguish about or divided this limestone. What kind of limestone is this? So we can know or clustering the possibility of the diagenetic process that can make the slope is more dangerous if there's full of water inside the pore of the limestone. Yeah.
Well,
yes, I agree with you. I think we can apply the other method by geological understandings.
Yes, correct, Sensei. Thank you,
well,
Sensei.
Thank you.
Thank you very much, Igarashi Sensei. Thank you very much, Yodi. Sensei, actually, Yodi is a young lecturer in UPN Veteran Yogyakarta. His major is geological engineering, and he is looking for a PhD degree, Sensei. So I think this discussion will lead to a detailed discussion. Maybe if you are interested with Igarashi Sensei, or Igarashi Sensei interested with the research, I will connect you too, so you can discuss for the research. I think that's all.
Welcome to Sapporo.
And Igarashi Sensei, thank you very much for your 30 minutes more. But,
thank you very much.
This is very insightful, and then we will continue for the next speaker. The second speaker is Dr. Carlito Tabelin. For Igarashi Sensei, once again, thank you very much, and
thank you very much.
Thank
you very much. Bye bye.
See you. Sensei.
See you.
Dr. Carlito Tabelin, are you there?
Hi, Shofa. Can you hear me?
Of course, you are very
Okay,
handsome
good.
today.
That's great.
What makes you handsome today?
Because we have a conference. That's why I have
Okay.
to wear my suit.
Thank you very much. But actually, the time is a little bit delay, and you can blame Igarashi Sensei for the delay. It's about 15 minutes delay, so you can blame him. You can blame him actually. So this is Dr. Carlito, and wait a minute. Actually, he has expertise in environmental geochemist, competent in the field of inorganic contaminant geochemistry, and also rock and soil water interaction, reactive transport modeling, mine waste water management, and prevention of acid mine drainage, and also the remediation of contaminant sites. He developed the two novel techniques, especially targeted pirate to limit acid mine drainage formation, and also his academic degree is actually from Mindanao State University, Philippines. Carlito Tabelin looks like Indonesian, but actually he is Filipino. So the first time I see Carlito in Hokude, I usually say in Bahasa, but actually he cannot speak Bahasa. So that's very funny for us. And he continued his master and also his doctoral degree in same with me in Sustainable Resources Engineering Division of Hokkaido University, Japan, with same supervisor, Professor Toshifumi Igarashi. But Carlito is very excellent. What makes him relevant to today's topic is Carlito very excellent. You can find many publications, about 100 publications, and also more than 2,000 citation in his profile. And he is now lucky for you, Carlito. You now join the School of Mineral and Energy Resources, of New South Wales in Sydney, and he is now working on sustainable mine wastewater management and also acid mine drainage prevention. And this 30 minutes, so you can use it for maybe less than 20 minutes is better, so you can save 10 minutes for participants for discussion. Okay, time is yours. Thank you very much, Igarashi Sensei. But now Carlito is talking. So please welcome Dr. Carlito Tabelin of University of New South Wales, Australia.
Thank you, Dr. Shofa, and good afternoon, everybody. I will try to speed up my presentation, just like what Shofa suggested, but I will try my best to finish it earlier than scheduled. So my presentation will be about lithium and copper for the green energy transition. It will talk about global resources, challenges, and possible opportunities. But before I continue with my presentation, let me take this opportunity to acknowledge my co-authors, Myla Villacorte Tabilin from MSU IIT in the Philippines, and Terayut Feng Saart from Chulalongkorn University. Climate change, as everybody knows, is one of the most pressing problems that is facing humanity in this century. So I found these posters online, and I selected them for this presentation because they look really powerful. It shows the three scenarios that were modeled by the IPCC, the International Panel for Climate Change. So what you can see here, this side here is when we succeed in reducing CO2 emissions, which is plus 1.5. And then we have this plus 2 means this is the 2-degree scenario. So in 2100, we will only have +2 degrees centigrade increase. And if we fail, if we don't do anything, then we will be in this area here. So what is interesting to see in these posters is that it says a lot about what will happen if we don't action or if we don't take action now. So we can see that the sea levels will increase, which is in this area here. The increase in sea level would make some of the coastal areas inundated with water, which means that a lot of people has to migrate. It can also cause coral bleaching because of the increase in CO2 concentrations, which will then affect the feedstock or the areas where fishes live and reproduce, which is a big problem for the food supply. And then we will be experiencing more of what we call extreme weather events. These extreme weather events include stronger typhoons. We have longer droughts, longer El Nino and El Niña, which is common in the Philippines and in Indonesia as well. Or we will have more widespread bushfires, just like in the US and in Australia. So because of this serious impacts of climate change, the UN and its member countries approve of the 17 development goals, global, the UN Sustainable Development Goals. So among the 17, number 13 is climate action. So what is this? What is the goal of this climate action? So basically, this is a continuation of the Paris Agreement, wherein countries around the world are tasked to reduce their carbon dioxide emissions and footprint. So there are a lot of sectors that release CO2 or equivalent CO2 into the atmosphere. So this is a pie chart showing the distribution or the distribution of CO2 emissions or equivalent emissions in gigatons in 2018. You can see here that the three largest emitters of CO2 are electricity and heat generation, mostly from your power plants. And then you have agriculture, and then you have industrial or industry. So industry here includes cement production, which is one of the biggest emitters of CO2, and also steel making plants, which also uses coke to convert ore to steel. So as you can see in this pie chart, the biggest one, which is electricity, and the fourth largest one, which is transport, these two have the best, or these two are the areas or the sectors wherein most countries can reduce their emissions. The reason for that is that in these areas, there are already alternative technologies. For example, in the electricity and heat generation sector, rather than using coal for power generation, it can be replaced by renewable energies such as geothermal, wind, solar, etc. While in the transport sector, rather than use fossil fuel-based cars or vehicles, we can use electric-based vehicles or EVs. So unfortunately, the industry and agriculture, we can't do a lot about this. But more in recent years, the cement industry are looking for ways to reduce their carbon footprint, while the steelmaking industry is now trying to develop ways to extract iron from iron ores using hydrogen. So if this can be implemented in an industrial scale, this might also reduce in better reduction in CO2 emissions. So although there is, although the clean energy and renewable energy sources are now in the mainstream, it still has one big challenge. So the biggest challenge when it comes to the clean energy transition or in the use of these cleaner technologies is that they are even more demanding when it comes to the requirements for minerals, metals, and materials. So this figure here shows a schematic diagram of the elements required for various technologies. So we have your fossil fuel technologies are here. So as you can see, it doesn't require a lot of elements. But then if we manufacture the renewable energy technology such as wind and solar, as well as clean energy or clean energy storage technologies such as batteries, then we would need so many more elements in it. For example, you will need REOs or REEs for the for the magnets of the wind turbines. We will also be needing a lot more of silver for your photovoltaic cells. And of course, we will be needing a lot of lithium for the batteries and copper for these other technologies. Okay, so for this presentation, although there were 17 elements or materials identified by the recent report of the World Bank that is important for the clean energy transition to succeed, I will only be discussing on two, copper and lithium. I selected copper because it's what we call a cross-cutting metal. Cross-cutting metal means it is essential for more than 8 technologies that is related to the clean energy transition. And then for lithium, it is an interesting element because if I'm not mistaken, Indonesia also has plenty of this, but they are not aware of it, most likely. So this is a pie chart of the production of copper globally in 2019. As you can see, there were 20 million tons of copper that was generated. Most of it came from Chile, Peru, and China. So Indonesia is also in here at around 1.7%. So most of the countries around the world or most of this copper are generated from porphyry copper deposits. So there are around 10 classifications of copper ores, and the most important source is of copper now is what we call porphyry copper deposits. So based on the projections for 2050, if we assume a 2-degree scenario, what happens is that the 20 million tons of copper that is required in 2019 will be increased to around 29 or 28 million tons of copper by 2050. If you look at this increase alone, it doesn't look so big. But if you imagine that humanity has generated around 550 million tons of copper for the last 5,000 years, that amount is needed for the next 25 years in order for the clean energy transition to succeed. So that's how much copper is needed for this, for the clean energy transition. So this is an example of what a wind turbine look like. So this is a 3 megawatt wind turbine. You have a 100-ton mining truck here. So if there are mining engineers in the conference, they would be able to imagine how big this is. So a typical human with a height of around 6 feet would be half of the tire of this truck. So if you can imagine how big this 3 megawatt wind turbine is, so it's really, really big. But then this is small because what is needed for the clean energy transition to succeed if we remove or phase out all of the coal-fired power plants is not a 3 megawatt, but a 12 megawatt. So you have to multiply these 4 times. So for the 3 megawatt smaller version of a wind turbine, we have, it requires copper of around 4.7 tons. And then it also requires other elements such as iron, you have aluminum, rare earths, of course, and zinc and molybdenum for the other parts of this wind turbine. Okay, so let's move on to lithium. So lithium, I'm sure, is very common for everybody. This is one of the most important element now because of the proliferation of portable electronics. So you can find it in things like your mobile phone, your wireless. I think some of you were wearing your wireless earphones. You have power tools, you have your laptops, and of course in EVs. So the projection for lithium is even higher. So the generation is around 70,000 tons as lithium in 2019, but this has to increase to over 400,000 tons by 2050. So there are a lot of issues when it comes to copper and lithium and its sustainability or its the resources that are available along the supply chain. So the supply chain is in your left. You can see materials are typically from mining and processing. You extract the metal and then you produce the goods. Once they are done, it is recycled sometimes. Sometimes they end up in disposal. So what are the issues and challenges for copper and lithium for the clean energy transition? So we will go into the three: sustainability, economics, and social environment. Let's start with sustainability. Do we have enough of copper and lithium? So this map here shows the distribution of porphyry copper deposits around the world. So take note, the distribution here is not of all copper deposits, but only of porphyry copper deposits. As you can see in this chart or in this figure, we have 14 of the largest, 14 of the countries with the most deposit of porphyry copper ores. So most of it are found in this area here in Chile. And then we have the US and Canada, and then we also have China. So you can see Indonesia also has big deposits that some are already being exploited while the others are not. So the big question here is, do we have enough? So the answer is it would depend. It would depend on the recycling rate. So remember, when we recycle things, we return materials back into circulation. So what happens here is that if we assume that we will only have a recycling rate of around 40%, which is the recycling rate for copper at the moment, this amount of copper, or the amount of copper available to us, will only last for 53 years. So then we have a big problem. Where will we get the rest of copper? So we have now, there are other options that we can do. Some of the richest people in the world are looking to space to get more elements. So if you're aware of Elon Musk and all those rich guys, they're looking at space. But then the most promising are not in space, but under the sea. So this is a map of where we can find copper underneath the ocean. So the important ores that are found in the ocean are these areas here, the green dotted one and the orange area. So the orange areas, you have your polymetallic sulfides. So these are very similar to those found in porphyry copper deposits, while this area, the polymetallic nodules, these are also similar to porphyry copper deposits. So these areas have potential deposits of copper. To date, there is one company that is trying to extract copper underneath the oceans. This area here, Solwara 1, is being exploited, or they are trying to exploit this area, and the company's name is Nautilus from Canada. So next we look at lithium. So lithium here, this map here shows lithium concentration or lithium resources around the world. There are two types. One are pegmatites. These are your minerals. And then you have brines, which are from your salt lake. And then this part of the graph here is the production. So this is the production per country. So the deposit, the country with the highest deposit is actually Bolivia, as you can see in this graph. But the problem in Bolivia is that their salt lake brine is not that good. So it means that production is not that high, and it's not very economical compared to its neighbors, Argentina and Chile. In terms of of minerals, the largest producer is, of course, Australia, where there are a lot of mineral deposits of lithium, specifically spodumene. So do we have enough? So for lithium, it's much better than copper. So if we assume we have zero recycling of the lithium from lithium-ion batteries, we still have 190 years to use up all of these resources that are available. So in case we will need more, there are, of course, unconventional resources that are available. So there are lakes in the US and China that can be exploited, but unfortunately, in today's technology, their concentration is still very low. The other one that I've mentioned earlier that maybe Indonesia is not aware or is aware of are geothermal brines. So geothermal brines can be an important source of lithium in the future. As you can see here, some geothermal brines in Russia, the Philippines, and the US have concentrations that are closer to the Salt Lake brines in China and the US. For minerals, it's very difficult to find other minerals aside from these three, spodumene, jadarite, and zinc-weldite. But then there are some wastes that may contain high concentrations of lithium. So these wastes are typically those that are from salt mines. So if there are salt mines in Indonesia, then it's a good place to look or to hunt for lithium. So unfortunately, some wastes such as coal fly ash or those that are found underneath the oceans have very low concentrations and are not good as resources. Okay, so next issue is on economics. Can we extract them? So extraction here means, can we make a profit if we try to extract this particular resource? So this is the typical flow chart when you have or when you are processing porphyry copper deposit. So you mine it, you process it, you have the concentrate, you send it to a smelter, the smelter extracts copper, and then there you go, you have copper. But then the problem now is that as high-grade ores are depleted, what miners are looking for are now the low-grade ores. So these low-grade ores, in order to be economic when you mine, is there is a need to extract not only chalcopyrite. By the way, chalcopyrite is the primary source of copper in an ore. You have to also extract the minor copper-bearing minerals. These include tennantite, enargite, and luzonite. So the problem with these three is that they contain arsenic and antimony. So these two impurities are not very good for smelters. So that's why dirty concentrate is one of the biggest challenges of the mining industry as of the moment. So there are no technologies, industrial scale technologies that are in place. So what the miners or the big mining companies are doing now, for example, Glencore, what Glencore is doing now is a simple, what do you call it? Blending. What they do is they blend dirty concentrate and clean concentrate so that the resulting arsenic concentration is less than the amount that is required by smelters. So that's the only way that they can sell their concentrate to smelting companies. So there is an opportunity in this area. So of course you can improve pyrometallurgical techniques in order to have a cheaper way of removing arsenic and antimony from the waste. But another way to look at it is not to use high temperature, but to use water or lixiviants, which we typically group into hydrometallurgy. So this is an example of a new technology that was released. I think it was released 4 years ago. By FLD Schmidt. This is an engineering company in Australia. So what the company did was to design a flow chart so that dirty concentrate can be processed using this particular flow chart. The key element here is this area, this part here, the media reactor. The reason why this is important is that if you leach chalcopyrite, what happens is that the surface of the mineral is easily passivated or coated with oxidized layer, which hinders the dissolution of that mineral. If you put grinding media, what happens is that it is removing all the oxidation layer, exposing new chalcopyrite for further dissolution. So the technique was pretty good. It can dissolve chalcopyrite for 6 hours at 96% efficiency, and it can even leach copper concentrate with low copper concentration. Generally, copper concentrate has copper concentration of over 20% for smelters. So even if it's less than that, this particular method can be used to extract copper. So next would be for lithium. As I've mentioned earlier, one of the biggest challenges when it comes to lithium from brines is that if it's of low concentration, then there will be a problem. The problem stems from this area here. So in order for the brine to be processed by traditional purification and precipitation, it has to have a concentration of 0.6 weight percent. So that's around 6,000 milligrams per gram. So that's how concentrated it has to be in order to be properly processed by a processing plant. So that's why in Bolivia, they have to have an extra step here in order to make their processing more economical. So the opportunity here is on the development of what we call selective lithium recovery. So the reason why concentration of lithium has to be high is because it is recovered using precipitation. So, you know, in chemistry, you need to have this certain concentration before a mineral can be precipitated. That can be removed if we can find selective ways of recovering lithium. So there are 3 that are promising. One is a selective precipitation technique developed in China. And there are 2 from China, actually. The other one is a layered double hydroxide technique. In this case, minerals or phases that are similar to clays are used. So the interlayer between these hydroxides can be used to capture lithium ion. And then if they are made magnetic, then recovery would be faster. The most promising one among the 3 is this electrochemical technique. So electrochemical technique, generally you can imagine of this as a reverse battery. So if you have a battery, you reverse it, then you can recover lithium. So this has been developed in many countries around the world, but the most successful ones are the ones in Korea. So they have developed a pilot scale to recover lithium from desalination brine. Challenge number 4 is in the processing of minerals. So the conventional way of processing minerals is this flow chart here. It's an acid leaching process. So the problem is that you have to use very acidic conditions, and the process is also non-selective. So the opportunity here is to develop alkaline leaching, which has already been shown by Outotec. This is the company from Finland. They have shown that it's possible, and they were able to leach spodumene in sodium carbonate slurry, and were able to extract over 90% of lithium with a purity of over 56%. So this is pretty good for a new technology.
Dr. Carito.
Yes.
Dr. Carito. Actually, it's about 30 minutes.
Okay, so let me just summarize everything.
Yes, please.
The final one is the socio-environmental part. So the biggest problem when it comes to new mine sites, especially for porphyry copper deposit, is the waste generated. So how big the waste are. So this is an example of a proposed tailing storage facility in Canada. This is the tallest building in Indonesia, Gamma Tower. So you can see how tall it is. This is the longest bridge in Indonesia, the Suramadu Bridge, and you can see this is the embankment. So opportunity, it can be repurposed via geopolymers or as as replacement for cement. And then the other one is acid mine drainage. So acid mine drainage is a big problem. It costs a lot of money to treat. It will take a long time to finish, and it contains heavy metals and carcinogens. So the opportunity here is to use acid mine drainage not as a waste, but as a resource. Basically, you can recover valuable minerals or metals in it. For example, the ferrite process developed by Professor Igarashi and company. So this is another opportunity, which is the development of new techniques like microencapsulation. So as a summary, for mining, there is also a new technique called precise geology. So basically, you are targeting only the ore and not excavating or mining the waste rock. So it reduces the waste that is generated. For processing, it's mainly on selective recovery and grade up. For the storage of tailings, to reduce the volume, we remove more water using tailings cake. Although it's more expensive, it reduces the footprint of the tailings storage facility. And finally, for acid mine drainage treatment, we go for passivation, or we can use it as a secondary resource. So this ends my presentation. Thank you for listening.
Thank you very much, Dr. Carlito Tablin. So that was very awesome presentation, Dr. Carlito Tablin, and I'm sure Jojo also has contribution with this presentation, but but I'm not here from him. He could not join this seminar or something, or he can join only in the night time. I don't know, but actually the important thing is recycling, and it is the answer, and then the key, and then the recovery of valuable metal is what Dr. Carlito already present. And I also here want to give opportunity to the participant. If the participant have a question to Dr. Carlito, you can write in the column comment. And also, if you want to speak by yourself, you can also raise hand and you can also speak. For your information, Dr. Carlito, our university, UPN Veteran Yogyakarta, has already a new concentration, new major concentration in metallurgy. So maybe if in the next future, we can also invite you as a guest lecturer, because I think it's more detail. There is more detail that you didn't explain. I think you can explain in detail in the guest lecture, so you can focus, and then the audience is more focused in your presentation. I think that's all. So it's already 12 past 5 minutes. But what is your time now?
It's 4:05.
Okay. I think that's all, Dr. Carlito. So maybe we can move to the next presentation. And Dr. Carlito, thank you very much for your time. That's very amazing. And then next time I will give you more time, maybe 1 hour for your presentation, and also 30 minutes or 1 hour for discussion. That's good for you.
Thank you, Shafa. Thank you for inviting
Anyway, please give applause to Dr. Carlito Tablin for his insight, and very useful, and also for his valuable time. Thank you very much, Dr. Carlito. And the next speaker is Dr. Omer Faruk Ugurlu. Are you there, Dr. Omer?
Hello from Istanbul, Turkey.
Hello, Dr. Omer. Can I call you Omer?
Yeah, you can call me Omer.
You already stand by maybe around 8 o'clock in my time, Western Indonesian time. I think in Turkey, what time it was?
Since 4 a.m.
So you woke up in the early morning this for this event, right? Yeah. So today, Dr. Omer Faruk will give a presentation about virtual reality in education from the perspective of mining. So he has over 5 years experience, maybe more, in mining and engineering research and teaching in Canada and also in Turkey. And he obtained his PhD degree from Department of Mining and Material Engineering at McGill University, Canada. So his research focuses on statistics, also underground mining, optimization, and also equipment reliability, and mine risk analysis and occupation health and safety mines, and also etc. And what makes him relevant? So for the participant, what makes Dr. Farouk Ogurlu capable of this research? The first, I think, is he is handsome. And also the second is he is graduated from McGill University, the best and also the best university in the world from mining research, I think. So Dr. Omar Farouk Ogurlu, maybe you have actually 30 minutes for a presentation, but if you can do it shortly, I really appreciate it. Thank you very much. Please welcome Dr. Omar Farouk Ogurlu.
First of all, I want to thank you for your compliments. And for sure, I'm going to speed up for my presentation. Thank you for having me today. I'm glad to be a part of this event. And my presentation is about a really hot topic, actually. And during the pandemic, we realized the necessity of technological tools in terms of education, actually. And let's share my screen. Okay, can you see my screen?
Okay. Yes, I think, yes.
Okay.
Please continue.
Okay, so second. Okay, the title of my presentation is Virtual Reality in Education from the Mining Perspective. And I am Dr. Ömer Farukoglu. I am a lecturer at Istanbul University, Cerrahpaşa. So I'm going to describe a problem, then I will give solutions, and I'm going to show some applications of virtual reality in specifically mining education, and I will give a conclusion. First, talk about a bit mining. Mining is a costly and hazardous operation in nature. When we look at this chart, we can easily see that mineral exploration, mineral extraction, and mineral processing are expensive operations. At the same time, drilling, blasting, and material handling are dangerous operations if you don't follow strict safety procedures. So for mining education, effective learning is crucial, because nobody wants to lose money, time, effort, and most importantly, valuable lives. So mining education contains highly challenging contents, such as planning complicated structures on the ground and under the ground, extraction and transportation of valuable minerals using heavy machinery systems, and also processing minerals with complex equipment and chemicals. So these contents are mostly carried out in the classrooms with 2D images and like low quality 2D images and videos. Therefore, students are exposed to the classroom setups which cannot be compared with the real experience. So for us, the most important challenge challenge for particularly mining education is transferring the theoretical knowledge into the practical work. So why this is a big challenge? I will tell you why, because there is a scientific explanation for this question. First, let me answer this question. So in terms of deeper learning and longer retention, which students will be more successful? The one on the top, student is reading and writing to learn, and at the bottom, it's me actually, doing an experiment to learn. So according to National Training Laboratory, there are two types of teaching and learning methods. The first one is passive teaching method, which is reading, writing, watching, being in a, like watching a demonstration. And the second one is participatory teaching methods, which is being in a discussion group. How can I do that? Oh, okay. Being in a discussion group, participating by doing and teaching others. According to the learning pyramid, which was created by National Training Laboratory, most students only remember 10% of what they are reading, but retain around 75% of what they are doing. So there's a big difference between two activities. So when we look at these two photos, we can easily say that the one at the bottom is doing something more important than the first one. So the interaction between human beings and physical world is necessary to fully understand and learn things. Because physical interaction and third dimension are required. So we know that conventional education lacks a visual of the third dimension and physical interaction. We already know it. And we have our traditional solutions, such as field trips, lab experiments, and internships. But as I said, this is our traditional solutions, and let's talk about field trips. So there are two different perspectives. One of them is the institution's perspective, the other one company's perspective. So field trips for the institution require a lot of effort, time, and money, because most of the time, minefields are located far from the living fields. So there are a lot of responsibilities to collect a bunch of students and travel from one place to another. And also the mining environment is full of like dangers. You have to be responsible and take care of your students and then come back with them. Also, you have to have a good connections to organize such trips. And we already know that like it's a really hard organization. And from the company's perspective, in your field, there are a bunch of students who are not trained well enough to be in the field. So you have to slow down your operation, and you have to take extra safety precautions. In addition to this, you have to assign at least one experienced person to show them around and answer their questions. Let's move on. What about lab experiments? So lab experiments require expensive equipment and prepared samples. When we look at the photo, we can easily see that the samples must have certain dimensions, like certain length and certain diameters. So you have to take like sources from the minefield. You have to prepare your samples for the demonstration, and you have to have enough sources to test the samples. Also, you need an experienced staff, and it takes also time and money. And most of the time, it's just a demonstration. And if you remember the learning pyramid, after the demonstration, students will remember just 30% of what they see. So students most of the time cannot conduct the experiments by themselves, and they're just watching the demonstration. And moreover, these kind of experiments are not suitable for collective training. So like a group of people, you cannot let them test the samples and such environments. So internships. We all know how hard it is for the institutions and also for the companies. It requires a lot of health and safety precautions, a lot of training with expensive machines, and it's a training. That's why you have to slow down the operation again. And for the mine, there is a limited access due to the safety measures for interns. And all in all, one of the most important obstacle for us is tracking the progression. For these 3 physical activities, we cannot successfully track our students' progression. So what is the solution? Let's talk about the solution. The answer lies in technological advances. Advanced technology provides innovative tools to overcome these challenges, while saving money, time, and effort. So recent developments in communication and information technologies improve equipment quality, and this significant change increased the ability of learners to interact with the information. So you can physically interact with the information by using these kind of tools. So our answer or solution for this kind of changes is virtual reality. So let's talk about virtual reality. What is virtual reality? Virtual reality is a fully immersed computer simulated environment that gives users to feel of being in a desired environment instead of the one they are actually in. And this technology surprisingly invented in the late 60s. And when you look at the photo on the right upside, this is the first virtual reality machine. And after some time, after some advancements, although it has been on the agenda since the late 80s, the use of VR was limited due to the expensiveness of the equipment. However, massive technology improvements have significantly increased the access to the VR equipment since the beginning of the millennium. So what we need to use virtual reality? Actually, there are different forms of virtual reality. I will just talk about the 2 of them. The simplest form, you just have a computer on a flat screen, and as a hardware, you are using keyboards and mouses. And there are some mouses, it's called like Air mouse, which is not the same as we are using now. It's a bit different. You can like lift in the air and change the dimension and change the movements and the location of the place. And also there are more advanced applications of VR. So the user is surrounded by a 3-dimensional environment, and using sensing gloves, virtual reality headsets, and clothes with sensors that you can see on the right side. And for the headset and the mouses, you can see on the photos. So let's talk about a bit about the applications. So what can virtual reality do for us? So virtual reality can provide virtual environments that are dangerous and expensive to train in the real world. Anybody heard Ferdano game? Ferdano is a virtual reality-based serious game about health and safety. As you can see from the photo, it's a simulation, and it's a game of rescuing an injured operator from an underground coal mine. So when you are playing this game, you are going to learn health and safety procedures and how to rescue a person from a dangerous place, an underground coal mine. This game is a digital and interactive underground mining environment developed in partnership with Ontario Mining Rescue Authority, Dynamic Earth, and NORCAD companies. And this game completed in 2016. So let's move on. So when we look at these photos, it's surprisingly that we can see the quality of the virtual world. It's so hard to recognize which one is the real photo. and on the left sides, these are the real photos, and the right sides, these are the virtual photos. And some of the applications I will show you later, you can even use the real photos in the simulation. So one of the most important benefits of VR is that you can easily track the progression, which we cannot make it with our traditional solutions. So beside the strong and weak points of the users can be determined successfully. We can see on the right side that when you finish this game, they can track your time, and they can track your decisions. And according to your decisions, game is going to determine your points, your score. In addition, the system can tell you the weak points, and the weak points can be trained by repeating the simulation again and again. And on the other hand, it cannot happen in the real life. You cannot create the same simulation in the real life and conduct again and again. It requires a lot of time, money, and effort. So think about our students. Most of our students are Generation Z, and they are familiar with these kind of technologies. They're playing video games, and by playing them, they're learning languages. They're making even friends. So why not teaching them by these kind of serious games? And we can easily adjust our curriculums and implement these kind of games in our classes. Oh, sorry. Okay, so we already talked about the obstacles of the lab experiments, and I mentioned that it's not suitable for collective training. But these kind of technological advancements, we can easily see that just with a headphone and the flat screen, you can feel that you are in the desired environment, and you can gain experience by being in this environment. And also for the lab experiments, we can create, let's say, like rock mechanics lab, and we can conduct our experiments, and we can easily track our students. So let's talk a bit about this kind of lab experiments on virtual reality environment. So this is a rock mechanic lab, which was created in 2019 in Hacettepe University, Turkey. It was a project of a research assistant called Kıllıoğlu, Dr. Kıllıoğlu, and he created this environment. By playing this game, you can test your samples. Let's say you have like a marble, you have like sandstone, and you can learn how to test these kind of materials, and you can draw stress and strain graph. And while you are playing this game, there are also health and safety procedures. And if you do any mistake, you can see warnings, and it's gonna cut your point. For example, when the machine is working and you want to open the door, you will see these kind of warnings that caution, the machine is currently in use. So it means that you cannot open the door. So while you are playing this game, you learn how to conduct such an experiment. At the same time, you are learning safety and health precautions. So you can create different scenarios, and by your decisions, the system can determine your points, and your teacher can easily track your progression. So this game can ask you to identify the hazard. So there is an oil split on the floor. So it might ask you to identify the hazard first. And then it might ask you to choose the consequence of what it can happen if you don't clean the floor. And also you can you can see the risk severity, you can choose the risk, and also you can choose the solutions. And based on your answers, your point will be calculated. So as we already know, like after the exams, it's hard to grade the exam papers. It takes a lot of time and effort, but for like with these kind of tools, it's so easy to track. It's just a second. When they finish their game, you can get the results, and it's so easy to grade our students by these kind of tools. And as you can see from this this figure, there are different scenarios, and based on these scenarios, your weak point and your strong points can be determined easily. So what about the internship and field trips? So by using virtual reality tools, you can you can bring the mind into your classroom. So look at this one. So this is a kind of a mine, a virtually navigatable mine. And when you create this, you can easily implement the real mining photos into your environment. And when you look at this photo and this one, you can see that the real photo is using in this environment. So think about that. Before going to this kind of places, dangerous places, you can gain experience by playing these kind of games and being these kind of environments. And when you are in the real field, you will be familiar with the environment, and if something happened, you know what to do. So if it's an emergency situation, you know how to solve these kind of problems, how to rescue a person from the mine. So this is a really like game changer technological advancement, specifically for education and mining education, particularly.
Dr. Omer.
So I'm gonna finish. This is my last word.
Okay, thank you.
I'm gonna conclude my presentation with Dr. Kızıl from University of Queensland. And according to Dr. Kızıl, virtual reality is becoming a vital means of education with the benefits of shortening the learning times while improving effectiveness, reducing the cost of education, and fully understand the necessity of the safety measures. So there are a lot of advancement coming in the future. And and you can play with this. So if you want to play, stay tuned. But I think do better and be a part of it. So terima kasih. Thank you.
Thank you very much, Dr. Omer.
I hope I am fast enough to finish the presentation.
Yes, okay. It's fixed already 13 minutes for you. But actually it's already 30 minutes, but I will let some participants to ask some question. If you have any question, please, you can ask whether to Dr. Omer, or if you still have any question to Dr. Carlito, if Dr. Carlito is still here, so you can also ask to Dr. Carlito. Please, for participant. Okay, Carlito, you are there still. Thank you very much. Okay, so I think I can conclude that for Dr. Omer, the virtual reality in education is actually can gain any experience in training class and also laboratory experiments. In my feeling, it's without any risk. So if we without any injury for the student and for the teacher, and also it is really fun. But the most important thing is how expensive is it? So if we invest in this virtual reality, like I think like PS5, PlayStation 5 or something, so we should invest something, right? So how much cost is it?
Actually, it used to be really, really expensive, like before the millennium. But thanks to advanced technology, it's getting cheaper. And if we consider that, like, for example, when you are going to a mine and you are using really expensive machines, it's not that expensive. So when you, let's say you are an intern and you are using a truck or a drilling machine, it's not as expensive as drilling machine. So think about that. Can you give an operator which has zero experience to this kind of like expensive machinery, or with, let's say, like 100 hours experience, virtual reality experience with this machine? Because virtual reality gives you opportunity to repeat the simulation again and again, and by using this, you are gaining an experience. And for the, let's say for the headset, for example, is not that expensive.
I see. I understand. Thank you very much.
Like in the long term, definitely it's cheaper than like the one. Let's say if there is a failure in the mine, think about that. How costly is it?
Yes, of course, it's cheaper than the actual things, right? Okay, let's move to Dr. Carlito. One question for Dr. Carlito. Actually, we talk about the recovery of the variable metal, and we talked about lithium and also copper, and how effective is the current research now. So I think we can say how many % we can recover from the things that something, or how effective is it? I want to know in quantity something, or in approximately something.
So you're asking about the efficiency of the processing, right?
Yes, that's correct.
So for example, for porphyry copper deposits, recovery in mineral processing is generally around 85 to 90%.
Oh,
so that
really?
means
That's
10% of of your copper ends in the tailings, are left in the tailings. And then for extractive metallurgy, I think it's also at around that level. And there are still some that goes to your fly ash and also in your slag. That's why there are research now that are being done to recover copper from the slag, because you can still have losses in the slag. When it comes to lithium, I think most of for spodumene, spodumene is not as difficult, not as difficult, but the differences between spodumene and porphyry is very how can I say? If porphyry copper deposits generally have around 0.5% to 1% copper, lithium deposits are more high grade. So you have around 4 to 5% as lithium oxide. And then when you do processing of spodumene ore, the upgrading is not so much. So from 3 to 4, it goes to around 6 to 7%. That's the only upgrade that you can get, because it's not so easy. For the processing, because it's leaching is typically more efficient than mineral processing. So that means you can get more than 90%, typically over 95% for hydrometallurgy. It's higher than mineral processing. So it depends on the ore, it depends on the deposit, it depends also on the processing technique that will be used by the operation. So that's the range of efficiencies when you process these kinds of materials. For recycling, it's worse. Recycling is very difficult. So it's less than 50. Maybe for recycling. It's really hard.
Okay. Difficult thing is about human capability or human competency, right? So
it's more on technology.
Okay.
For ore, because the technology has been there for more than 100 years, so we already have so much lessons that were learned. So the technology is very matured. When it comes to recycling, we keep on changing things. So the material is being changed all the time. So when you change the material that goes into the waste, the process has to be changed depending on the material. So that's where the problem comes in.
Okay, thank you very much, Dr. Carlito, for your nice explanation. And it's already past 7 minutes. I'm sorry for the committee. And thank you very much, Dr. Omer Faruk Ugurlu.
Thank you, Shofa. Thank you for that. Thank you, organizers of the conference, for inviting us.
Yes, you're welcome. And also next time I will invite you again, maybe. Okay, that's all for 3 main speakers. The first speaker is Professor Toshifumi Igarashi and also Dr. Carol Tablin, and the last speaker, it's already close with the virtual education by Dr. Omer Faruk Ugurlu of Istanbul University, Serapasa. And then it's about time, and then I'm sorry for the late, and I will close this session with thank you very much for investing your valuable time, and I will return to the MC. Dayu, Sarah, are you still there?
Thank you very much, Dr. Sofa.
Okay, I will let you handle this time. Thank you very much.
Thank you very much, Dr. Sofa, and all speakers for inspiring us the knowledge about mining and environment.
This event sponsored by PT Studio Mineral Batubara, Pusat Studi Mineral dan Energi, and Riung Mining Contractor. We are now entering break session. The duration will take about 13 minutes, and we will continue to first parallel session at 13:15 Western Indonesian time.
you.